What I would like to do in this talk is tell you what I think are the exciting things going on in cosmology these days. It's a subject that you see in the newspaper all the time. I think there's lots of interesting basic science that can be conveyed through studying this topic. You can use it sort of as an excuse to learn some fundamental things about the electromagnetic spectrum, about gravity, all sorts of things, mainly things with sort of physics related interest. Cosmology is I know is often would be taught as a small section in a course. If a school had a course on astrophysics or astronomy, this would be a tiny piece of the whole topic. What I like to think about when I teach cosmology is the broad historical perspective to it and try to connect it into things that you tend to see in a more standard astronomy course. So in particular, this is easy to do these days because many of the modern developments in cosmology are, in a sense, as I will try to show you today, are part of a Copernican revolution, sort of a new Copernican revolution. We are in the middle of a complete rearrangement of our understanding of physics and astrophysics and cosmology. Okay, let me show you something that I'm sure you've all seen before, but I always find this to be awe-inspiring. This is the Hubble Deep Field, a deep integration on roughly a few arc-minute patch of the sky, taken by the Hubble Space Telescope now some 6 years ago. And it's a photo that was the deepest integration that the Hubble Space Telescope had made up to that point. And what you can see here in this, it's a color picture as taken with different filter bands on the telescope. You can see some very old things. And cosmology is essentially a study of how did the universe evolve, how did it begin, and by using data like this, it's possible to try to answer some of those kinds of questions. So what you see in this picture, do you have a pointer of some kind?
Here, I got a laser if you want.
Okay.
Never leave home without it. You gotta take the safety off.
Thank you. Maybe it's still on. Oh, there we go. There we go. So I like this picture because it shows an entire zoo of different kinds of objects that you'd see in the universe, starting with relatively nearby galaxies. So these large swirly things here. You can see directly here they have different colors depending upon their temperatures and the kinds of stars that are in them. But these big things are relatively nearby. This object here is actually a star within our own Milky Way galaxy that is extremely bright, and merely because it's nearby. But then as you analyze this, you can look at some very faint blue objects in here and red objects. If you could measure the distance to these things, and this is the subject of a tremendous amount of work by astronomers, you'd learn that some of these objects are several billion years old. And so this is, in a way, a snapshot to some of the earliest things that we can see in the universe. Now, it turns out that this is nothing. And what I want to spend most of today talking about is light that you can't see in this picture. It's microwave radiation that's coming almost directly from the Big Bang. And while the most distant objects you can see in here come from perhaps some of the first stars that were formed in the universe, there is light that exists that comes from much, much farther back in time, nearly to the Big Bang itself. And so I like this picture because it gives a nice perspective, an overview to the objects that are in the universe, but in fact, cosmology deals with things that are even farther away, things that you can't see with an ordinary optical telescope, or even an extraordinary one like the Hubble Space Telescope. Now, one thing that you can learn from these galaxies is by looking at their distances and their velocities. You find something that's been known since the 30s, that the universe is expanding, that the more distant galaxies in this picture are receding from us nearly at the speed of light. And so this is known as the Hubble expansion, which is Edwin Hubble was able to get his name on a telescope for inventing this idea. And the idea was totally shocking in the 30s, but it tells us that the more distant an object is, the faster it appears to be receding from us. And this rule, this Hubble law, as it's called, governs all of cosmology. So everything I talk about today will be based upon our living in a universe where the contents appear to be expanding in all directions. I'm going to spend a lot of time trying to explain what I mean by that. Question?
I was recently, there was on this, what they call the dark energy, pertaining to the supernova, A, I think it is, work that was done, and the idea that it's actually speeding up rather than coming to a rest and then coming back in. It's actually speeding up away.
Yes.
So.
Okay, and I'll touch on that a little later. But this picture, I'm talking about the expanding universe, used to immediately beg the question, well, if it's expanding now, is it ever going to stop or perhaps turn around? And it turns out that until just 3 or 4 years ago, the answer to that was not known. And it appeared that the universe was slowing down, but we couldn't tell whether it was going to slow down enough to actually turn around or not. Now, with the measurements you're talking about, measurements of distant type 1a supernovae, we get a precise measurement on the distance to some tracers that are in the universe. And those seem to tell us that the universe is not actually decelerating, but is actually accelerating. And so I'll talk about that a little bit later. Okay, that is part of this Copernican, or this new Copernican revolution I want to push on. Okay. Okay, now last year, Sanjay and I sat down and decided it was time to make a tutorial, an online tutorial about cosmology. And if you go to our webpage at this site, and this is also linked through the Space Science and Engineering Center sites here, you can get to our tutorial, and I will do that for you. Put this aside for the moment. Okay, and it appears on the web page for my research group over in the physics department. Down here is the cosmology tutorial. Okay, now this was written by a sophomore undergraduate, a physics major here, and her name is Molly Reed. And what she did was twofold. She developed this web page, but at the same time she was working on an outreach project to middle school students that Sanjay had running last summer. And so in the process of trying to explain cosmology to these students, she developed this web page. And this web page has some videos, some movies that she took of these students asking questions and getting excited about cosmology. So she did such a good job that I'm going to go through this in some detail. The goal was to make this available to anybody, and now it is available, both as a resource for students, perhaps who are just trying to learn on their own, but also hopefully something that might be useful to teachers. And we tried to make the level very broad. So there are things in here which will be certainly well below the high school level, and maybe some things that would be beyond it. So what I'm hoping is that this, if you are thinking about introducing this particular topic of cosmology into a course, this might be a resource that you could use. On our web page, there are lots of other links to other sites that have more in-depth tutorials about cosmology. There's so much going on. Lots of people have decided to try to do a good job at this. Okay. Well, let me just go through this and touch on a few things that might be helpful for you. For starters, this picture and then the one that I showed you before of the Hubble Deep Field, it reminds me of how I like to start talks about cosmology, and that is I usually have my pocket full of pennies, and I pull them out and I throw them on a table and say, this is the universe in front of you. And basically that's what it looks like. If each penny represents a galaxy, they sort of scatter about 10 penny diameters apart in some random order on the table. That's more or less what the universe is. It's made out of galaxies. Those are the luminous things in the universe. And they are more or less scattered at random. This is an example of just one galaxy, similar perhaps to the Milky Way in which we live. But if you want to have a sense of what the universe on large scales looks like, it is mainly stars inside of galaxies, which are separated by fairly large distances. Okay, so here are things that are found in typical astronomy textbooks about the history of astronomy, the problems that the ancients had in trying to understand the unusual motions of the planets against the background stars. And so that's an interesting way to start. The problem is I find for most students that this becomes a source of some yawning. I mean, it's an interesting exercise to work out how the ancients tried to figure out how they could build a universe with the Earth at the center and then everything moving around it, a geocentric universe. But what I think is really exciting is then is to switch now to the heliocentric universe that Copernicus suggested and see how suddenly all the difficulties disappear. And it's this kind of Copernican revolution that I mentioned before and I hope to get back to later on. Okay. So anyway, the Aristotelian and Ptolemaic models we talk about here. I'll skip through here a few things. Let me bring up something. How many people here know what the Olbers paradox is? Olbers paradox is you may have heard it in a different form. Is this that we know our model is that the universe is full of stars and galaxies. We think that the universe goes off infinitely in all directions, or at least large distances. So why is it that as you look out from the Earth in any direction in the sky, why isn't that you do not see something bright in all directions? Why isn't the sky bright at night? Or in other words, why is it dark at night? And the answer to this has to do with the Big Bang. The model we have for cosmology today, including this expansion I talked about before, tells us that the light from distant galaxies is, for one thing, is shifted by the Doppler shift to red wavelengths. And so the most distant things aren't even visible within the wavelengths that your eye can see. So that's one answer to this paradox, which is one piece of evidence for the expanding Big Bang model that is commonly taken today.
One way that I like to present this paradox is to say that any line out from the Earth has to end on a lit up point if there's an infinite space and infinite number of stars. But another way to look at it is that any line that leaves the Earth does reach a lit up point. It's just that it's lit up in the microwave part of the spectrum.
Okay, that's I think a very clear way to put it. And that, I think Molly did perhaps a better job at explaining this than I did, but that I think is a good way to put it. That, well, yeah, all lines of sight eventually end on something, but if we have a universe that is expanding, then it turns out that the distant things will look redder than the nearer things, and so red that they're in fact in the microwave part of the spectrum, as you pointed out, and not even visible to the naked eye. So this is something that was brought up in the last century, but only people thinking about it now have really begun to understand the answer to that paradox. Okay. Well, I mentioned the Hubble expansion before, and this is, I think, perhaps the most fascinating thing about cosmology, but also the thing that is perhaps most difficult for people in general to understand. The way I like to think of it is as an expanding balloon. And in fact, later on, there's a little video of how you can make a balloon and inflate it and put galaxies on it and see how things expand apart from each other. And it's a very graphic way to imagine the expanding universe. But the idea is in this balloon analogy, which is strictly an analogy. It's what we imagine is that the universe we live in is, in this analogy, we imagine we live on a two-dimensional surface, the surface of this balloon. And I like to tell students that they should pretend that they are ants, and they are only allowed to crawl along on the surface of this balloon. Some students who have read Flatland sometimes have another way to view this analogy. But the nice thing about this picture is that if you constrain yourself to stay on the surface of the balloon and not allow yourself to move towards the center that is off the balloon or away from the surface of the balloon out into space, then this two-dimensional universe is actually a fairly useful approximation to what we live in. And that is this balloon expands, all the objects on here move apart from each other. The more distantly separated objects move away faster, and you can actually, sit down with rulers and expand this thing and pretend every second you're expanding it by the same amount. You find that the expansion speed close by is small. Out here, it's very large. But perhaps the key thing that this demonstrates is that in this cosmology, this Big Bang cosmology that seems to work so well these days, there is no center to this universe. That is, ignoring the center of the balloon, which we call a point that you're not allowed to go to, there is no special point on the surface of the balloon. And so any galaxy or any observer in one of these galaxies is totally equivalent to an observer in any other galaxy. And so what in our little demonstration, you'd have students pretend at random, say that this is the Milky Way, and they could draw a circle on this balloon and measure the radius of that thing, and then expand the thing and watch how that circle stretches out. But they could have chosen any other point on the surface and get exactly the same answer. And so this is a way to try to demonstrate something that is called the cosmological principle. It's something that is, it's an assumption about the universe that seems to be true, that the universe looks the same on average to all observers. And so if we just happen to live in a galaxy that is, so to speak, on the other side of the universe, whatever that means, we would in general see the same kinds of things we see here. That is, universe is expanding. We would see the Hubble expansion, more distant things recede from us faster. In detail, things would be different. We wouldn't see the Milky Way, or we wouldn't see the Big Dipper, for example. We wouldn't see specific arrangements of stars and planets that we do on the Earth, but we would see in general stars. We would see galaxies. The big picture would be the same. So this, there's one other nice thing about this analogy, and that is that I've drawn here a surface which is not flat. And so if I constrain myself to make measurements or to travel only on the surface, I have to somehow account for the fact that this is a curved surface. And this is a fact that we have to deal with in the real three-dimensional universe. The universe we live in is curved, but for a different reason than this. In our universe, the curvature comes about because of gravity. And that's going to get me to this point about the mass and energy in the universe. It's directly connected to gravity. Yes, Mike?
Now, if this is a three-dimensional universe and there's no center, it's curved in some other direction?
In the real universe?
Yeah.
It's curved in a direction that you can't see. And that is,
It's a four-dimensional universe?
there's a fourth dimension which you can't visualize.
Perhaps more.
There may be more, but in order to make this picture work, you only need to imagine at least four. The hard thing for most people, including myself, is going from this picture, which is easy to see, and somehow imagining that this same kind of thing is true in a real three-dimensional universe. You just can't draw the thing. You can't draw this curved three-dimensional object. So the analogy becomes very important, and this I think for many cosmologists is the working picture they carry around in their heads, because this is something you can visualize. This is an example of what would be called a closed universe. It's finite, so in principle you could set off in one direction, and traveling long enough you would eventually come back to where you started. Or if you're receiving light, in principle you could actually receive light from yourself. That is, you would see you're behind as you're looking off in this direction. You'd see light coming around from the other side. That's not actually observed as far as we know in the universe, but that could also just be because this balloon can be as large as you want it to be. So it may be light hasn't had time to make this full circuit around the universe, but it still could be closed. There are measurements that you can make, and this is towards the end of the talk, that tell us that in fact the universe we live in is not curved very much. It looks like it's almost, well, the best analogy I can make is a balloon that is extremely large. And so in any local region here, this balloon looks to be almost perfectly flat. Okay. Now there are other geometries you could have, and I'll show those a little bit later. So the Hubble law, which I mentioned before, comes about in a very natural way on an analogy like this thing here.
So if you were to say at what point did the Big Bang occur, the answer is everywhere.
Everywhere, and that is something that I've been trying to argue with my in-laws for years. It's one of these things that comes up every Thanksgiving, and I can't quite explain it. So I'm going to have to bring the balloons next time and see what I can do. Or maybe refer them to my tutorial here, or our tutorial. Okay, this is another way it's often put. Molly tried to bake some raisin bread to make this work. Unfortunately, the loaf, as I understand it, came out very badly, and so she didn't want to put an image on our webpage of it. But to try to carry that analogy into three dimensions, the thought is, well, imagine that you are inside a loaf of bread with raisins in it, and this thing is in the oven, and it's expanding as it cooks. And you choose any one of those raisins to represent your home, and you look off at the other raisins in the bread, and you see, well, they are receding from you as the thing expands. And this analogy breaks down because there is a center to this loaf. But if you were embedded in this thing and you had no way to get out and you didn't know where the edges were, you would see this effect happening to every raisin in there. Okay, you would, unless you can see the edge, there is no way to know that there's a center. So if you had a very large loaf of bread and you were inside of it and the raisins were expanding, you would reproduce in some crude way this Big Bang expansion with no center to it. Okay. Okay, and now we're beginning to see a piece of this little demonstration you can do, which can be quite exciting. Inflate the balloon, get a giant balloon, have the thing pop at the end of the class, that kind of stuff. I always enjoy doing that. Okay. Well, the neat thing about this expanding universe is that we can try to make a timeline of it. And this is a graphic that I grabbed from one of my favorite web pages, which is also linked to our web page here. This is a timeline of the universe in this Big Bang theory. And so on the bottom here we have time going from t equals 0. The next instant here is 10 to the minus 32 seconds. So unimaginably short amounts of time. And then we're way out here at some perhaps 15 billion years. Pretty good guess for the age of the universe. And not to scale for sure. The neat thing about this expanding universe is it's an amazing tool. First of all, because it allows us to look back in time. We're able to see light from, for example, these first galaxies, like I showed you in the Hubble Deep Field. That light travels at the speed of light and reaches us. It's been traveling for most of the age of the universe, as maybe 10 or 11 billion years. These things formed at roughly 1 billion years after the beginning. But we can see in the Hubble Deep Field most of the contents of the universe that are illuminated, that have stars, that are bright. Okay. Now, we can run this movie backwards, though. So we can only see so far. But if we imagine that the expansion, which we now see pulling everything apart, if we were running that expansion movie backwards, we could go back to an arbitrary early time and imagine things piled on top of each other. And this has become an enormously powerful tool for physicists, because we can pretend that if we go close enough to time t equals 0, that the universe had an arbitrarily high density or arbitrarily high temperature, all this corresponding to an arbitrarily high energy. And in fundamental physics, people are trying to understand how do particles interact at extremely high energies.
You say an arbitrarily high energy or a arbitrarily high energy density?
Well, both. Because if we look at if we made a graph here of any quantity, density, energy density, temperature, anything related to energy.
I'm probing here about the idea of conservation of energy. Does the universe have less energy right now than it did at that time, even though it was more condensed?
The universe doesn't conserve energy, at least in this model. The things that are making the universe expand we don't understand. And we can think of that as something from outside that's being put in that makes the thing work. So we don't have on the largest scales, we don't have a way to use our most fundamental assumption about physics, and that is energy should be conserved. It doesn't appear to be in the universe.
Okay, so it's not conserved, so it has decreased?
It is, let's see.
If it's accelerating, I would think it would be increasing.
Right. The energy has increased since the beginning, and exactly that, for exactly that reason you're talking about. There's some accelerating effect, and that, again, I hope to get to that before we're done. Okay, that is added energy to the universe. Anyway, if you're interested in how fundamental particles interact when they collide at energies that aren't accessible to any accelerator that could be built on the Earth, you can just say, well, let's hypothesize that maybe there's some remnant information from the very beginning of the universe that might answer that question. Okay. So The universe, to many physicists, is sort of the poor man's accelerator, high energy accelerator, for getting to energies that are just not approachable on the Earth. Now, the thing I want to talk about today, in the last half of today, is this region here. I mentioned the microwave radiation, microwave background radiation, that comes from a time far earlier than the time when stars and galaxies existed. And so this time here, about 200,000 years after the Big Bang. So this is a time when the universe was hot, but stars and galaxies hadn't formed yet. And the universe was just full of hot gas, hot enough so that it was ionized. And so most of the universe is made of hydrogen gas, and so we have this picture of just ionized, nearly uniform, hot hydrogen plasma, just an ionized hot gas. Now, the neat thing about a hot gas is that it's opaque to photons. So out here, the universe is cool enough that in between the galaxies, there's mainly vacuum. There may be some gas, but it's neutral gas. Whereas back here, things are hot enough that we have only ionized gas. And as I said, that is opaque to photons. So in that Hubble Deep Field picture I showed that we could see back to this time, if we wanted to see farther back in time, we'd have to choose a different wavelength, which the Hubble Space Telescope isn't sensitive to. That would allow us to see back to about this time. But before that, there's a fundamental barrier, and that is just that any photon, regardless of its wavelength or energy, can't propagate through a universe that is this hot and this dense. So we have what is sometimes called the cosmic photosphere. There is, at a large distance from us, a surface that is emitting microwave radiation, or what we see now is microwave radiation, and it is telling us what the conditions were like at that very early time, about this time. In fact, it can tell us about things going on way back here. There will be subtle imprints from the beginnings of the formation of galaxies and clusters of galaxies that come from way back here at this time that's called inflation. Those fluctuations that eventually became the structures we see in our universe now were present here and left some very faint imprint back here at this time that we call parting company. This is when the photons were able to decouple from the hot gas that they were embedded in before that time.
Okay,
Mike.
so we can see these primordial photons that go back to this 200,000 year period because that's when the decoupling occurred.
That's right.
Is there a similar flux of neutrinos that goes back to an earlier time when that decoupled?
Right, so exactly. So if we were to go back to, we know neutrinos can travel through matter with hardly ever interacting. They can travel through the sun with hardly a chance of interacting. But as we go back farther and farther in time, the universe becomes more and more opaque, higher and higher density. And it turns out if you go back to just a few seconds after the Big Bang, this is a time when now even neutrinos are unable to travel very far without being absorbed by matter. And so if we could detect neutrinos, we could, in principle, use them to make images of what the universe looked like way back at this time. The problem is nobody's figured out how to detect these particular neutrinos, which form sort of a sea of particles that bathe us from all directions in the sky, but we just can't detect. Mike?
Would there be a graviton flux from an even earlier time?
So this is the neat thing. This picture keeps going, and so before neutrinos we go to other things, and gravitons actually would be right back at the very Big Bang. This is something that's of course the topic of tremendous speculation. If there are gravitons, particles that give us gravity, they would have been emitted copiously back here.
So people talk about, as I sit here, I'm being flooded with billions of neutrinos every second.
Right.
But they're of such an energy and such a quantity that I'm unaware of. Is there a similar type of an idea then that there is a flood of gravitons? That's
Exactly.
what you mean?
Right.
From that very early time?
From that very early time, surrounding us everywhere, but not detectable yet. It turns out, oddly, that there's more of a chance of detecting those than the neutrinos.
Really?
So I won't talk about this much, but there are two ways to do this. One of them is through large gravity wave detectors on the ground and then ultimately in space. They have a chance of detecting those gravitons. The other way is actually if there are gravitational waves or gravitons that were emitted early on, they will have some effect on the microwave background radiation, which I want to talk about today. This is even though we cannot see directly through this period back to the beginning, there will be imprints of things that happened early on the microwaves.
Using the tools of the cosmologist, can you predict what the wavelengths of these different fluxes, just like you predicted the wavelength of the photon flux?
Yeah, you can. It turns out that this neutrino background that comes from here, everything is known about this except it isn't detected. The energy of the neutrinos would be comparable in energy to the microwave photons in the microwave background radiation, which I'll talk about in more detail. The gravitons I don't remember, but they would have a predictable spectrum. So people know almost exactly what to look for, but they just don't know how to do it. Okay, so this timeline I find to be very helpful. And so Molly has rigged up some things here to explain a little bit about some of the physics involved in this epoch called decoupling. That is, these are photons which, when we have neutral helium and hydrogen gas, they can mostly travel right through. But before that time, when things are too hot, the photons are scattered. They're absorbed, and so the universe appears opaque. Okay. Okay. Now, okay, so this is, oh gosh, I don't want to show this, sorry. Okay, so at this point in most of my classes, I spend a lot of time talking about something called black body radiation, which is the radiation that comes from any hot or anything with a temperature. And the microwave radiation from from the Big Bang has a spectrum, which is a black body. It's a particular kind of spectrum, which has a characteristic wavelength of a couple of millimeters. And it turns out that for a black body, that the wavelength tells you immediately what the temperature is. So it's the same thing if you do a demonstration of the hot burner on a stove. Something that is glowing red has a known temperature, and you can figure out what it might be. Hotter things will have shorter wavelengths, and so the surface of the sun is glowing away in the visible part of the spectrum, sort of right in the middle of the visible. And so that's at shorter wavelengths than the glowing stove. And then you'll hear later this week, my colleague, for example, Dan McCammon, will talk about hot things that are actually emitting X-rays. Again, just because they're so hot, the wavelengths come out shorter, higher energy photons. But here we're talking mainly about microwaves. This is the radiation that we detect from the microwave background radiation. And so as you see here, it's a couple of millimeters wavelength. It's on the same order as the wavelength that you get out of radar systems and your microwave oven. Okay.
Out of curiosity, would there be longer wavelengths than microwaves resulting from the Big Bang?
Not from that time that I showed. So the radiation we get from that era has a full spectrum that ranges. It peaks at millimeter wavelengths, but it ranges way out to radio wavelengths. It's a complete spectrum, but it's all coming from that time. Times earlier don't give us any photons. They're just stopped. Okay. Well, okay, so if you map the sky, looking at this radiation, the microwave background radiation, you get a plot that looks like this. These are actually hot and cold spots that are visible on this cosmic photosphere, this time a couple 100,000 years after the Big Bang.
How much variance is displayed there?
So, I'll show you this picture again in a minute, but the difference between the hottest spot and the coolest spot is very small. It's about a part in 100,000.
Wow.
So this map is a little bit deceptive. The radiation we see from this early time is actually almost perfectly uniform in the sky. And it's one of the things that we think tells us that it has to be cosmological. Any radiation source closer to us, like our own galaxy or galaxies nearby us, would have more radiation in one direction than another. To make something this smooth, somehow it has to be built in some fundamental way to the whole structure of things.
So when Penzias and Wilson first discovered this, I mean, their equipment was not accurate enough to see the variations. They could only see, no matter
Exactly.
which way they looked, it all looked the same.
That's right.
It
So
wasn't until, what, Kobe?
this is a map from the Kobe satellite, about 1990. That was the first to definitively show that there were faint differences in temperatures. This is often called the ripples in space-time in magazines and stuff.
Is there also a slight redshift due to the Earth's motion?
There is, and that's not shown here. The Earth is traveling through this black body radiation, and that effect would give a Doppler shift, so that in the direction that we're heading, the wavelengths would be slightly shorter. Things would look a little hotter than the direction behind us. That effect has been subtracted out of this map. It's thought to be sort of a local effect. And so
in effect, you could determine the relative velocity of the Big Bang.
you could. So in a sense, there's sort of a rest frame. There's a coordinate system in which the microwave radiation is not at rest, but expanding uniformly or traveling uniformly, and the Hubble expansion is expanding uniformly. And we know that our own Earth is moving with respect to that frame because we're cycling around the center of the galaxy. Our own galaxy is moving. So in these maps, that sort of local effect gets subtracted out.
So as time goes on, would the wavelength of this shift longer then?
Progressively longer
As
and
it's-
longer.
as it's-
That's right. So it is, when it was first emitted, the matter that was actually radiating the photons was roughly the temperature of the surface of the sun. Surface of the sun is actually to a good approximation, a black body, and it's ionized hydrogen. If you were to cool the surface of the sun very much, it would become neutral and would become transparent. But the sun is hot enough that that doesn't happen, and it looks opaque to us. It started off as nearly visible light, which has now been redshifted into the microwave part of the spectrum. Okay. Well, let me leave Molly's overview behind and focus more specifically on these modern things related to the CMB, cosmic microwave background. And let's see. Okay. So I mentioned this black body spectrum. This was also measured by the Kobe satellite. And this is something that's not as well known, but an amazing achievement. So if you plot up in the form of these data points here, the spectrum measured of the microwave background by something called the FIRAS instrument, far infrared spectrophotometer. You get this curve here, you get these data points here, and then the solid line represents the theoretical curve that you expect for this object called a black body. And it's a perfect fit. It turns out that even in the laboratory, you can't create a black body that is as closely closely follows the theoretical curve as this one. And like I say here, here's the wavelength. The peak wavelength is a couple of millimeters. But as you asked before, the wavelength, it's a broad spectrum. And so there's information out here at radio wavelengths, several centimeters to meters. There's no cutoff, actually. And then it turns over, and there's radiation out here in the far infrared part of the spectrum.
So you're saying that the Kobe image, the actual black body radiation, matches the theoretical curve exactly?
Yes. So if you looked at any one of the pieces of that map I showed before from Kobe and measured the spectrum, you would see something that looks exactly like this. And the places that are hotter would have the spectrum shifted just by a tiny amount towards shorter wavelengths, and the colder spots would be shifted slightly the other way. But in either case, they match what's called a black body spectrum. Their temperature would be slightly different. Okay.
As time goes on, the peak will shift in this diagram to the left.
Yes.
And also drop down.
Exactly.
Okay.
Okay, so there are two things we always teach our students about black bodies, and one is the peak is proportional to the temperature. The peak wavelength is inversely proportional to the temperature. So as time goes on, this will shift to the left. Temperature is getting colder as the universe expands, and this whole thing will start to collapse and become the power, the amount of the intensity of the radiation will fall as the temperature drops. This paints a rather grim picture for the future of the universe. It's going to be cold, and it's going to be even darker.
Just like Wisconsin.
Like Wisconsin in the winter. Okay, now if I were fair and showed you on a fair scale that ranges from 0 temperature to 3 Kelvin, the temperature representing something to do with the intensity, if I took that Kobe map and plotted it in those units, this is what you'd see. The sky is totally blank. But if I amplify the faint differences, the faint signals in there, I begin to see interesting structures. And so this is what Kobe measured. So this is a picture, it's a map made in what's called galactic coordinates. And I imagine you'll see a lot of this stuff this week. In this coordinate system, our own Milky Way galaxy appears across the center band. The actual center of our galaxy is here, but all directions in the sky are somehow included on this egg-shaped thing. Now the red stuff here is radio emission from our own galaxy, and so that gets subtracted out of these so-called Kobe maps before you see them. This is nearby stuff that's obscuring our view to large distances away. But these things out here, where the galaxy is fairly thin and transparent, these really are faint temperature differences that come from early on. And so the temperature range here is like 18 microkelvin. This is the variations from the 2.7 Kelvin black body curve that I showed before. So if you clean this up once more, you get back to this picture that I showed before. The galaxy thing has been taken out, color scale has been changed a little bit, but sure enough, a hot place like here is a place that was slightly denser back at an early time in the universe, slightly denser, slightly hotter, and so the radiation from that direction in the sky carries that same temperature difference that it began with way back at an early time.
Can they come up with a good explanation why the lumpiness?
Yeah, okay, so that's one of the, if you go back to that timeline that I showed, it appears that these lumpy things come about from physics that happened almost at time t equals 0. This process called inflation is a quantum mechanical process. And in quantum mechanics, we have the uncertainty principle. I'm just waving my hands here, but this is the way it's explained to me. Fluctuations happen. Okay, and those fluctuations, random fluctuations, give rise to what we see here. So even though this is coming from still not the earliest time in the universe, it's showing us stuff that happened at 10 to the minus 32 seconds, at least in the
And so
modern
the
picture.
areas where it's the warmest is the most dense, so those would be areas of galaxy formation?
Ultimately, these are still large things.
Yeah.
These would be places where there would be many clusters of galaxies. But yes, in general, there's more stuff here, and that would evolve into places where there's a concentration of matter. Yes,
Okay,
Mike.
let me try this again. The Big Bang, the fluctuations just kind of happened at the Big Bang, like things don't necessarily explode in an even sense. And
That's a good way
why
to think
things
of
are
it.
lumpy.
Yeah,
Okay.
it happened at the very beginning, the thing that we call the Big Bang.
Do we have any idea or any guess as to the dimensions of the universe at 10 to the minus 32 seconds?
There are, people will tell you, I forget what it is offhand, but some tiny, very tiny length. I mean, again, as you approach zero,
Less than a light year.
much less than a light year. I mean, so the size is, well, so the physics that we think gave rise to this happened after 10 to the minus 32 seconds. The size that the universe was then, I don't know, but it was well below atomic dimensions.
So our understanding of the probability of quantum mechanical fluctuations leads us to this particular sort of blotchiness rather than a smaller or larger blotchiness.
Well, there's something left out here. This is the smallest blotch you can see on here is limited by the instrument that made the map. So since that satellite flew, we've realized that there's much more information at smaller scales. A more finer resolution is what you need in order to see those things. And I'm going to step to that right away. Turns out there's much more exciting, well, this is exciting enough, but there's more going on at smaller angular scales.
So that Kobe map was taken at about 10 to the minus 32 seconds?
No, so it has, the origin of the hot and cold spots in here comes from that time. The photons that actually we detect with our detectors are coming from about 100,000 years after the Big Bang.
So that's about 100,000 years
Right.
ago? Or from the Big Bang?
From the Big Bang. So from our perspective, this is most of the age of the universe backwards in time.
So, what's the name of the woman who's been mapping the galaxies? Margaret
Geller.
Geller.
Yes.
Geller?
Geller.
So, we look about us now and we see large areas where basically it's like bubbles within the universe where there is nothing.
Yes.
And kind of like the galaxies are located with string work on the surface of the bubbles. So, in other words, like if we're looking back at this, the hot areas would probably be areas where big strings of galaxies formed, and the cool spots where the bubbles are.
Exactly that. That's and so the measurements that are made looking at galaxies and so forth by people like her are things you make with optical telescopes, and you're looking at relatively nearby things compared to this. But one of the miracles of cosmology is that we can connect this very old light to these things that we're seeing nearby, and so we can. It's exactly the same.
Jive when you take into account the time and path.
That's right. So it turns out that the largest kind of clusters of things that are seen in these galaxy maps are on scales that are smaller than this thing can see. But I will show you shortly a map that is more commensurate in size. If I can.
Okay. You might be going to answer this, but okay. What size does a microwave dish need to be in order to get the angular resolution of, let's say, the Keck telescope?
Oh, okay. Well, the difference is, let's see.
Like your dish out there is what, about 16 foot in diameter?
It's 8 feet in diameter,
8
about
foot.
half of that.
What would that be comparable to in optical wavelengths?
What's the scale of
Um,
that? Light is what, 5,000 angstroms?
right.
Red light is.
Let's see. Well, I could, okay, so the,
Are you talking the lambda over D relationship?
I guess so.
Rather
yeah, so there's two things going on. One is we're looking at different wavelengths, and so
Right.
they're so we're at a wavelength of a couple of millimeters instead of, say,
Couple of angstroms.
or well, half. There's about a factor of several thousand in wavelength.
Okay.
So to get the same angular resolution as Hubble, we would need to be 1,000 times bigger than the Hubble dish, which is like this.
95 inches. I
Right.
think.
So we can't do that.
Yeah, so can
but-
you do with microwave scopes, like they've done, like with the very large array?
With an interferometer.
interferometry?
That, yes, you can start to get to the same angular resolution that way. And that can be done. But the other thing we're doing differently, of course, is we're looking at a very different time. And let's see. So the things that we are, well, I'll explain this map in a bit. This is a higher resolution map than the Kobe map. But still, the features in here are about a half a degree across. So this is many tens of degrees along the side of this box. And the hot and cold spots in this picture are roughly a half a degree, about the size of the moon. That's about the angular resolution limit of this particular instrument.
this was a balloon board.
This is a balloon-borne experiment. So these still are enormous in size. They represent enormous volumes of mass compared to, say, a galaxy or even a cluster of galaxies. So within this, there's a mass concentration that today would include most of our observable universe. Okay, so we're looking at very different scales. So, but still, we believe there's a correspondence between the differences in temperatures here and the structures we see in our universe now. So this is a higher angular resolution version of the Kobe map I showed before. And once again, these are temperature differences that come about because of variations in the density and temperature of the matter at this early time. Okay. Now, it turns out that there is a way to measure the geometry of the universe from this. And now I'm trying to come back to my original topic about the modern Copernican revolution. And let me see if I can explain this in a clear way. So we believe that the reason that most of the spots in this map are about the same size. Well, let's step back. If you analyze this map, it turns out, your eye can fool you because you try to form patterns, but it turns out most of the patches in here are about this 1 degree size. And so you can do an analysis of this map and form something called a power spectrum that tells you that most of the information is from clusters about a degree or half a degree across. And that turns out to make sense within our Big Bang model, because we think that between the time that the universe began, t equals 0, and the time that this radiation was emitted toward us, that about 100,000 years passed. And just doing some very simple calculation, you would say, well, in 100,000 years, the biggest mass concentration that could form could be about 100,000 light years across. We have to assume, or we still assume, that nothing can travel faster than the speed of light, including information about gravitational pull from matter in different parts of the sky. So we think we know that each one of these blobs represents something that is about 100,000 years. Real good question. We think we know that because of the, actually because of the temperature of this radiation. So in our model, we thought it started off as radiation that was visible light. We know now that it looks like it's microwave radiation. And that, you can think of the reddening of that light is either coming about because of a Doppler shift, because it's coming from a source that's receding from us, or a more helpful way to think of it for computing distances is that it tells us that the universe is expanded by a factor of about 1,000 from the time it was emitted to the time we received it. In this this Hubble expansion, it turns out that all the distances between galaxies stretch, but also the wavelength of light that's traveling through it stretches. So it's another way to think about this redshift. It's, you can think of it as just a stretching between the peaks of the waves and the photons. Anyways, that stretching factor that we think we understand well, because we know the original spectrum and we know what it is now, and that allows us to compute this distance. So that turns out to be 12 billion years times the speed of light. And so we've put together a little triangle here. We think we know L. We think we know big L. We measure theta. And what all of this has assumed in my picture here is that we're in a flat universe, that we are allowed to use the rules of ordinary geometry on a plane. Now, if you remember, early on I was showing you pictures of trying to live on the surface of a balloon, which is a curved surface. And it turns out that the geometry of the universe depends upon how much matter there is in the universe. If we live in a very heavy universe, then the geometry, it is the geometry that the light paths, that the light has to travel across, will be closed. So this is a high density universe. We have a geometry that looks kind of like that thing that I showed you before. It looks like a two-dimensional closed sphere. And if we are observing from here, some object way over here, exactly this picture here, the light paths actually go in a funny way. This just has to do with drawing lines on the surface of a sphere. Turns out that this angle theta would be bigger than what we would have if we had a flat universe. So this is a high density closed universe. The picture that I've drawn up here, so this is separate from this. This picture here represents a flat universe that is geometrically flat. And then you can even imagine a low density universe. This is very hard to picture. It would be called open, in which you have the opposite of a sphere. And so instead of things being closed around, this is usually drawn as something that looks like a saddle. It's kind of a floppy surface. And we pretend here that we have light paths traveling on this sort of this open surface. And it turns out that in that universe, photon paths travel on curves that go like this. What that means is the geometry of the universe will have an effect on the actual angle, the angular size that we see these things on the sky. So if we lived in a closed universe, the curving of the photon paths would have made these patches bigger. And if we lived in a low density open universe, they would have looked even smaller. Well, it turns out because we can complete this triangle and ordinary plane geometry works, this tells us to a very good approximation we do live in a flat universe. We don't have these curving effects on the light paths. This is a very hard thing to imagine. The way I usually I try to explain it is that the in 1919, there's an expedition that was inspired by Einstein to go out and look for light that was, he predicted, would bend around the sun from a distant star. And it turned out he was right, that light is bent by gravity. And this curving of the light paths from early in the universe is the same effect. It is light being bent, the light paths are bent by the presence of matter in the universe. But instead of the case that Einstein talked about, where you had the sun and then you had a distant star and the light would do this kind of a thing as you observe it over here, this is a case where the universe is just full of matter everywhere. There is no concentration of it in one place or another, yet it still has an effect of curving the light paths. And so it's this measurement here, this picture, that, that was presented just a couple of years ago that tells us that the universe we live in is geometrically flat. And because the curving of the light paths has to do with the amount of matter in the universe, this also tells us exactly what the density of the universe is.
Peter, let me just ask you a question, if I may. Try to reconcile two different concepts, and I'm not quite sure how to get explain this. If we live in a flat universe, and we are observing from our vantage point, and in every direction that we look, the radiation is uniform, that by isotropy implies that our observation limits tell us only that as far as we look, we are seeing as far away in every direction due to the essential uniformity that you just showed. So that leads to the concept that it's spherically symmetric.
That's right. Or,
And how
yes.
do you reconcile that with the concept of a flat universe?
Okay, okay. All right, so this is in many ways a confusing notion. It is still three-dimensional and uniform. And by flat, I just mean, I no longer mean, are we living on the surface of a sphere or are we living on a plane? Those are just analogies in one lower dimension and two dimensions that I appeal to. Flat here just has to do with, we're trying to now extrapolate up to 3 dimensions. And flat just means, does light that sets off in a straight line appear to continue in a straight line?
And that leads me to ask the next question, in that, what would be the essential difference then between this and at least what the original concept of what was a steady-state universe? I mean, is that getting closer to the steady-state universe concept, where it's not?
Okay, we'll talk about dynamics in a second. What happens to the expansion? But it's possible to be expanding and still have this geometry that and here flat just means that light paths don't bend. That's really what we're getting at there. It doesn't mean that we live on a plane. Okay, Mike?
There's a geometrical argument that I use in my class, and I'd like to test it on you, because maybe it's wrong.
Okay.
And when you're dealing with the 2 dimensions, you can say things like, a flat piece of paper, the circumference is 2 pi r. But if it was curved like a balloon, it would be less
That's
than 2 pi
right.
r. And if it was curved like a saddle, it would be more.
That's right.
So if I generalize to 3 dimensions, now I'm talking about the surface of a sphere, which is 4 pi r squared. But it would be more than that if it were curved in one way, and less than that if it
That's
was
right.
the other way.
You-
And that's what we mean by flat.
That's it. Okay, that is, so what you've been able to do is move from 2 dimensions to 3 dimensions. And in fact, you're right. If you could actually make this measurement, if we could actually travel around space and measure, go out there and actually measure the distance on the surface of a sphere,
Large enough.
on a large chunk of space, if we could actually measure the surface area and show that it's the same as what you'd predict, 4 pi r squared, assuming that you lived with normal Euclidean geometry, the geometry of uncurved space, then you would have proven that you have flat space.
Now, if there was some naive giant in such a space, might they be tempted to redefine the value of pi?
Oh, that's an interesting question. I think not, because the effect is something you would only see on big scales. You wouldn't see it in small parts. So there would be
a small distortion on a small scale and a large distortion on a large scale.
So
they wouldn't scale equally.
Right. So the giant, as long as he could make measurements on different scales, would realize, something's going on here. That there's something happening in the geometry and not my value of pi.
Okay.
Okay. So.
Thank you.
Okay. So I think that's an excellent. You sold me on that analogy. So the last thing I want to talk about is this business about density. So matter curves the path of light. We have some evidence from these maps, very strong evidence in fact, that there's not enough matter in the universe to curve the light. Well, there is just a certain amount of matter. This, the amount of matter that gives us a flat universe. And it turns out that that matter is usually spoken of as a density. We live in a universe where the density is equal to something called the critical density. What does that mean? So this map would look different if the universe had more or less matter in it than it does. And so this thing called flat implies that the density is equal to something called the critical density, which is 1 times 10 to the minus 29 grams per cubic centimeter. On average, if you could spread out all the matter in the universe, you would have this amount per cubic centimeter. This is what we mean by flatness. If the density were bigger than this, then we have what's called a closed universe. And as I mentioned before, these spots would have been bigger. And if we lived in a lower density universe below this thing called a critical density, it would have been what we call an open universe, and we would have had small spots. Okay.
Is this where dark matter comes in?
This is where dark matter comes in, and this is where I want to close.
Now, closed would be oscillating universe. It would eventually start contracting, and open would just keep on going.
This is a bizarre thing that I'll get to in a second. It is possible to, a few years ago, that was exactly what people believed, and this is the way I was trained. But it turns out that it is possible to have a universe which has less than the critical density, but could collapse, or a universe that has more than this critical density, and it could expand forever. And I'll try to get to that in a moment. This is the modern Copernican revolution. Okay, so let me try to explain what I mean. So the question is, what is this matter? Now, a proton is about 10 times less massive than, well, the mass of a proton is about 1.6 10 to the minus 30 grams. So this is a very low density, but gravity interacts over enormous distances. So if we, and the universe is huge, so even with such a low density as this, there's a gravitational interaction between all matter and other matter that has an enormous effect on how things expand. And as we look over the whole universe, even though the density is low, we have a hard time accounting for the matter that this seems to imply. So usually the way we express this is in terms of a quantity called omega. And omega is the ratio of the density to this magic critical density. And we now think of the universe as being made up of several different kinds of species of things. And so this rho, this density, has contributions from different kinds of matter. One kind of matter is called baryonic matter, which is just a physicist's name for ordinary matter. The Earth is made out of baryonic matter. People are. This is just neutrons and protons.
Quarks and leptons?
Quarks and leptons at a more fundamental scale. So in fact, the observable universe, gas, hot stars, all of those things are baryonic. Turns out, when we go around and try to add up all the matter that we can account for from observations, this only is about 5% of the total mass, or total density of the universe. It's actually less than that. We can infer that there are other things present. And so we have a density that we think comes from something called cold dark matter. And we know about this not because it glows or is visible directly, but because in clusters of galaxies, this kind of matter has to be present in order to keep the thing gravitationally bound. So we can see how the visible light, visible objects are swarming around in a cluster of galaxies, and we have to infer how much total mass was there to keep this thing from flying apart. Most of the mass in such a cluster turns out to be dark, and we call it cold dark matter, because not only does it have to be dark, it turns out that it doesn't interact well with other matter. Okay. And so cold is just another way of saying that it's slowly moving, and this particular kind of matter is not something that's easy to detect. Nobody has directly measured what this is. So this represents about 30%, we think, of the critical density. And so we're trying to come up with a critical density that's this. Most of it is not visible light or things that we know. Most of it is, well, either in this form or now the last part, which I'm going to add here, which is I will call dark energy. And this is the most mysterious of the whole bunch. And this might be 65%.
Now we're adding energy to our little formula here, which is supposed to be telling us about the density of stuff.
Yes. So
this is using Einstein's relation?
yeah, so I freely allowed, if you'll remember Einstein telling us that energy is equal to mc squared. Mass is directly related to energy. This is a substance we prefer to think of in terms of energy, but we can also, if we want to, convert from energy to mass, and likewise to mass density, which is what I have up here.
Might it be possible to consider the primordial photons, the primordial neutrinos, and the primordial gravitons as energy that contains some contribution as well?
You could, it turns out you can, if you included those, it would be a very tiny part of this
Way
picture.
smaller than any of the-
Even smaller than this. So I've actually left it out. But for completeness, I should include other things that we know and love. So this row might have row of photons and neutrinos and gravitons and so on. Turns out these are a very small fraction of the density of the universe when you convert them to energy units, or to density units. This is the thing that has become most exciting recently, this dark energy. And so I want to get back to a couple of questions that came up earlier. These, these objects here all respond to gravity. So they are attracted to each other by ordinary gravitational forces. This doesn't. This mysterious dark energy, which has got lots of other names, is something that has energy to it, but actually is actually repulsive gravitationally. There's something about it that causes it to repel from itself. And so this makes up the, the largest fraction of the density of the universe, and is actually appears to be driving the universe to accelerate in its expansion. So up until a few years ago, the game was to try to understand how this stuff affected the expansion rate of the universe. And if you wanted to know whether the universe would expand forever or not, you just needed to determine what this density was. It now appears that that's only a very small part of the iceberg. That, in fact, there's this mysterious part of the components of the universe that dominate the dynamics of the universe, that actually make the whole thing expand and accelerate. I call this the Copernican revolution revised, because it used to be people had this nice, neat picture of what the universe looked like. The Earth was at the center, the sun went around it, and you could rig things up, and you had this complicated model. And then suddenly somebody said, all right, let's put the sun there, and everything becomes clear. The step in doing that, the step that we had to make in that revolution, was to take ourselves away from being at the center of the universe. We had to allow ourselves not to be special. And we have to do that again here, because in fact, we're not even made out of what most of the universe is made out of. We have to completely rethink our thinking about what our place is in the universe. We are only a very tiny part. We are made out of baryonic matter, and we not only are not made of what most of the universe is made out of, we can't even detect it directly. That completely puts cosmology on its head. And what I like about this is that it's real out of the box kind of thinking. You know, what could be more bizarre than this? So I'm going to skip the rest of these things here. I want to get right to that apparatus you saw at Pine Bluff last night if you were out there. This is during the daylight, and I'll try to explain what we were doing. We're actually trying to make maps of the sky, looking at those small patches I was talking about, the microwave background patches. And with this custom telescope, which is designed specifically to make that kind of measurement, we are able to make some maps like that. And we haven't yet analyzed the data, so I don't have pretty pictures to show you. I can show you how the work goes on. Here's one student, Slade Klavakovsky, who's a PhD graduate student from Stevens Point, Wisconsin. And so this is his PhD thesis, trying to operate this telescope. So what you saw was probably this, which is just inside of this screen here. The screen is trying to prevent radiation from the Earth and from the sun and the moon from getting into the detectors. Down here you see another student, hard to see, he's cold. His name is Phil Faris, and he is a grad student at Santa Barbara who came up here. We convinced him to come here for the winter to help with this experiment. But anyway, this thing, which is 8 feet across, is concentrating on looking at the microwave radiation from near the North Celestial Pole, right around the North Star. And we stared at that spot now for a couple of years, trying to detect the hot and cold spots in the CMB there. What you see back here at the focus of the telescope is a very sensitive radio receiver, which is tuned up just for the wavelength at which these microwave radiations are radiation is very bright. And then this is just to put things into sort of a larger perspective of what we do here at Wisconsin. That experiment you saw is called COMPASS. We are working on a whole range of other experiments or detector technologies, but all of them aimed at trying to understand this microwave radiation. Okay, with that I will close my presentation on cosmology and the new Copernican revolution. Thank you.